In the last video, I described what it meant to be an angle by saying that it was two rays joined at a common endpoint. We also talked about what it meant to go from one of those rays to the other in either direction, either on the inside or the outside. It matters where you start and where you end, but it also matters which direction you go in. We can measure these angles much more easily if we start with our initial side or our initial ray as though it's set going along the positive x-axis. That means it's centered at the origin, and that's our common endpoint. And then our terminal ray is somewhere else. It can be anywhere. It could be there. Let's see, it's a different color. It could be down here. It could be over here. But if we call this our initial ray, or if we always set this up so that the initial ray is along the positive x-axis, we call that angle in standard position, or we say that that angle is in standard position. This is not the only place in mathematics where this is common. For example, if we're talking about calculus 3, we can take a vector anywhere in space, anywhere on the xy plane, and move it so that its tail starts at the origin. We call that a standard position for the vector. Now, this isn't calculus 3, so you don't need to worry about that. But I want to make the point that that standard position is a very useful kind of starting place. It's also common, or standard, to start at that position but move in the counterclockwise direction. Now, I'm old, so I remember clocks that look like this. The hands of a clock always move in this direction. The minute hand, if you will, moves more quickly, and the shorter, I made that a little too long, didn't I? The shorter hour hand moves more slowly, but they both move in this direction, so we call that clockwise. And if we're going in the opposite direction, we call it counterclockwise. Depending on which videos you're looking at, when you're watching mine, I'll probably say counterclockwise, but in the UK and in a lot of other Commonwealth countries, they call it anti-clockwise. Anti meaning against. So counterclockwise and anti-clockwise means going in the direction not that the clock would go, an analog clock would go, but the opposite direction. So here we're going to go anti-clockwise or counterclockwise, and that's our standard. Okay, it's going to feel backwards if you're familiar with analog clock, but that's our normal for trigonometry. All right, back to this diagram. I have an angle. It starts here on the positive x-axis. That's my initial side. And it goes, it looks like about 60 degrees or pi over 3 radians till it gets to here. So this is its terminal side. Now I'm going to draw another angle. Oh gosh, it looks like it's the same angle. It's starting at the x-axis and it's ending in the same place. But watch what happens when I show you how far it's traveled. It's actually gone all the way around and then gone a little farther. So this angle, if this angle is the smaller white angle is 60 degrees, this larger angle is 60 degrees plus 360, or as I like to think of it, 360 plus another 60. That's 420. So I have a 30-degree angle, no, a 60-degree angle, sorry, 60-degree angle, which is pi over 3, and a 420-degree angle, which is 7 pi over 3. Don't worry, you'll see how I get there in a second. And they're not the same angle. This is clearly much bigger. But what we can say about them is that they are coterminal. Their terminal angle is the same. So if I'm going to be working with a 420-degree angle, I might as well be working with a 60-degree angle. Now, in some applications, it really matters that 420 is not the same as 60. 60 is just a little bit. 420 is a lot. It's all the way around, plus a little more, plus another 60. But you can see that they land in the same place. So let's see if we can find an angle that's coterminal to 45 degrees. Well, looking at the diagram, if this pink angle, this big one here, is coterminal to this smaller angle, the white one, they just land at the same place. They start here and they both end here. But the pink one had to travel an extra full circle to get there. So if this one's 60 degrees, then how could I figure out what the other one was? Just add 360 degrees to 60 degrees. So another way to find an angle coterminal to 45 degrees is to start with the 45 degrees and add 360. That's 405 degrees. So an answer here is that an angle coterminal to 45 is 405. Now let's find an angle coterminal to 3 pi over 5. Well, 3 pi over 5 has a pi in it, so I'm working in radians. If I want to add a full circle to 3 pi over 5, I can't do it in degrees, I have to do it in radians. Well, a full circle in degrees is 360, but a full circle in radians is just 2 pi. If I put that over 1, find a common denominator, I get 3 pi plus 10 pi over 5, which is 13 pi over 5. So an angle coterminal to 3 pi over 5 is 13 pi over 5. Now, there's no rule that says we have to add a full circle. We can also subtract a full circle. So another angle that's coterminal with 45 degrees is 45 minus 360. And another angle that's coterminal with 3 pi over 5 is 3 pi over 5 minus 2 pi. When I do this arithmetic, I end up with negative 315 degrees. When I do this arithmetic, I end up with negative 7 pi over 7, or negative pi. In both of these cases, what's happening is that I'm starting in standard position. So I'm starting here. I'm going around 45 degrees to get to one version of the angle, the 45 degrees. But to get the coterminal angle, I'm going out 45 degrees and then subtracting 360. So I'm doing this from 45 degrees. So I go out 45 and then I come back 360. So another name for this angle is negative 315. And another way to draw it, let me get a different pen. Just stick it in here. I'm not sure how I ended up with yellow, but that's okay. Is to say starting in standard position, go backwards 315 degrees, and that puts you there. You end up in the same place, but we went a different way this time. I could also have subtracted 360 degrees twice or 3 times and still ended up in the same place. Just like over here, I could have added 360 or 2 pi multiple times and still ended up in the same place. It's not uncommon to use the Greek letter theta to represent an angle, and oftentimes you'll see that inside the angle you're demonstrating. So to find a coterminal angle, we could say that the angle theta plus or minus 360 degrees times n being an integer, so any number of multiples of 360 is coterminal to theta. We could also say theta plus or minus 2 pi times n is coterminal to theta. And that's just because 360 degrees is a full circle more or less than the original angle, and so is 2 pi. So we can either add or subtract, and that's really quite handy because, first of all, if you start with a small angle and you add 2 pi or you add 360 degrees, you could add or subtract 360 degrees or 2 pi multiple times and end up with multiple coterminal angles. Equally, if you subtract multiple times, you can get multiple coterminal angles that way. But what if I give you an angle that's really big? This angle is clearly in multiples of pi over 4, but it's 23 pi over 4s. 23 pi over 4s is way more than one full circle. One full circle is 2 pi. So in pi over 4s, that would just be 8 pi over 4s, or 8 pi over 4. That's one full circle. So if we subtract 2 pi, we get 23 pi over 4s minus 8 pi over 4s. That's going to be 15 pi over 4s. That's still more than 8. So let's do it again. Let's subtract 2 pi in the form of 8 pi over 4. That gives me 7 pi over 4. 7 pi over 4 is less than 2 pi, so having subtracted 8 pi over 4, which is 2 pi, having subtracted that twice, I've got to an angle that's less than 2 pi, so it's somewhere in the first rotation, and therefore 23 pi over 4 is coterminal. 23 pi over 4 is coterminal to 7 pi over 4. It's also coterminal to 15 pi over 4, but one of the reasons that this skill is useful is that it lets me get to an angle that's somewhere in the first rotation, right? It's somewhere less than one full circle. So this video has been about standard position, but most of it has been taken up using talking about coterminal angles. But we couldn't really talk about coterminal angles if we didn't have a common starting place. So the idea of standard position is really quite important. In the next video, we're going to be talking about the length of a circular arc. A circular arc doesn't have to be in standard position, but I personally find it quite useful if it is. In that video, we're going to be talking about length of a circular arc, which leads us to a very common and very important formula.